take some time before. Good, good. Yes, it works good. So then I go to my Zoom. Uh, how do I go back to my Zoom? Yes. I minimize this and go here. So I trust that you can see my PowerPoint, right? Could you raise your hand if you can see it? Oh, good, good. Thank you so much. So today we'll start our journey with Global Environmental Change course, which has been very popular. And also we'll continue our journey uh, about and around this course. Since this is the first day, I love to give you some of the preliminary information about the course. So this course, every Tuesday in Norway, 2:15 p.m. It will take place always in the Zoom, and there is a password there, the ID there, and passcode there that you all have already come in. And I am the course responsible. And if something happened to me or anything happens, then there is a Professor Jens One who will be teaching some part of the lecture also, and also taking over from me in the later part, should there be necessary. And for this course, those of students who have joined it for taking entire course and also going to give exam, every lecture there are mandatory special reading material which is posted in Canvas that you'll see. In addition to that, always in this course, there are exchange students, there are many other students that participants who do not have any kind of prior environmental science background. For them, we also will be posting some of the basic material that is taken from the book Environment 9th editions or 8th edition. And because this time is a corona and it's not easy to get, so the amount of pages which is allowed to copy, I'll be keeping under each lecture, where this is some part of book as a supplementary reading material, so that you can understand a little bit of what is the basic things that we are talking about. This book looks like this, and this is available, I think, in the library, but you don't need to buy at all, because I'll be putting the page limit which is allowed by the publisher, the copyright, following the copyright law, some specific pages from here and there in the books under each lecture. Those NMBU students who have enrolled have access to Canvas system. This is our learning management system in Norway, here in the university. So when you go to Canvas, what you should be doing is press module there. Then, of course, before if you want to come into the Zoom lecture each time, press the Zoom, and in that day you click start. This is only for NMBU student here in Norway, or those students that are enrolled here. And if you press module, then you get this screen here that I am showing, and this screen. And then Under lecture, for example, today is 8th of September, and I'm introducing global environmental change. And if you click on that one, if you click on this one, then you get this one. So there, after this lecture, I'll be keeping this link to that video that I've been talking all through here. And the reading material, mandatory reading materials for understanding of these lectures are here, these two. And then the core is this one, my PowerPoint that I have also put it here. So all links are there. And those other students who are in Nepal, Bhutan, who are also from our partner projects country, they will get this material through their teacher. So it's no worries. And there is a supplementary reading material anyway. So in this journey for this global environmental change course, we'll be talking very many different topics. First of all, the relationship with the earth environment have changed, and it has been changed in many ways, hundreds of ways. We cannot cover that entire topic of global environmental change in this kind of introductory course, but at least we have selected something which has relevance for today and relevance for our type of student that comes to an MBU. And this is also relevant because in developing countries like Nepal, Bhutan, Pakistan, that we are also supporting through No Red project, these students also have this kind of topics, and their coordinator will suggest them which of these Tuesdays online lecture they should take, which is relevant for their studies. So in this particular lecture, I'll be talking about introduction to Earth system science and global change. What is really a global change? If global change is only climate change or it also consists of other things, and how the Earth system science is there to teach that in which way this Earth system science is providing clue for many natural and anthropogenic change at the Earth system level. That means combining different kind of spheres which are there in the Earth system, including biosphere where you live, and hydrosphere, all the water bodies, lithosphere, all the rocks, and uh, that kind of system where the rocks and all those things are all, soil is also a part of that system. The pedosphere is above this lithosphere, and also most importantly, cryosphere also. And in this entire course, we'll be talking in a greater detail about what kind of anthropogenic influences are there in our system. And we also talk in a rather little greater detail on ecosystem processes that are relevant for atmospheric and global change. That means atmospheric ecosystem processes like carbon cycle, nitrogen cycle, methane, nitrogen cycle, which is very important for three important greenhouse gases like carbon dioxide, nitrous oxide, and methane, which contributes almost 90% of predicted global warming. And we'll be talking also a land degradation, which is also a global environmental change issue because it has international policy responses, and land degradation is taking place in such a magnitude, such an extent that it is affecting a large part of human population around the world, and therefore it is also a issue, the topics of major topics of global environmental change. That also will be teaching in future lectures. Very important global water challenges and also the glacier melting, a little bit about the hydrological processes and what are the current emerging and future global water challenges. It has been said that future war will be not because of inter and intra-state conflict, but it is because of the water issues that will be taking a little bit around that one. And then, of course, as I say that in order to call it global, that must also have some kind of international policy responses, international activities, and will bring some of the initiatives like what is happening with the Paris Agreement, why this other agreement before that Kyoto Protocol didn't work that well, and also there will be a separate lecture on biodiversity convention because from the natural science perspective, biodiversity loss is even more serious than the climate change. Then we'll also talk about bit about the soil and soil resources, particularly focusing on carbon sequestration, how to bind, how to bring back that carbon which is there in the atmosphere in order to buy time, in order to have some kind of mitigation that can be done at a farm level. A farmer can do it, and also all at different level one can have a kind of approach and also kind of strategy for carbon sequestration. Then there will be something around life cycle assessment where how your behavior, how different things that you produce in order to have a better life and in order to do things very quickly, where they comes from, what is the energy footprint of that one, and where it's end up. Even though the technology that we are using now, mobile phones, this and that, if you look at how much of carbon footprint, energy footprint, these in the entire life cycle from production, for acquisition, production to use, and then when you throw it away, that kind of idea around life cycle assessment will introduce that one. Also, there will be a very specific lecture on a global food crisis, global food production and security. What is actually issue around the food production, whether it's issue of production or excess or the quality at different part of the world in a more global context by a very esteemed colleague, Professor Ruth Hogg. Of course, there are other lecturers which are coming to take these courses. And we also talk about finally all the global environmental change is a human construct, mostly anthropogenic, but now it's hurting back to human being. So it is like a boomerang. So we'll talk about the human health issue in relation to global environmental changes, particularly climate change. And we'll talk also a lecture on transformation and sustainable future, because after all, whatever technology people are aspiring, whatever uh, things, incremental change in the innovative technology is really not catching the pace of global environmental change and the harmful effect of that one toward human, which is a self-created problem. So what kind of transformative change is required in our behavior, in our attitude, if you want to even dream about the sustainable future? And that there will be also separate lecture on that one. So this is all about just introductory thing, what we are going to cover in this entire course. So before I continue further, all of you are sitting, stop looking to your screen for a moment and just close your eyes. Close your eyes, all of you. You slowly, something called resonance breathing. Take breathe in, breathe out. You may count around 4 internally without producing any sound. Just say, when you breathe in, 1, 2, 3, 4, 5. Pause, breathe out, 1, 2, 3, 4, 5. From nostril, you breathe in, breathe out, breathe in, and breathe out. you continue for 1 minute before we continue, because I've been told that looking these Zoom kind of things, after a while, students start getting fatigued. So we need to do some other practices, something around it. Okay. Continue to breathe in, breathe out. Okay, you may gently open your eyes and look around this side, that side, up and down, little bit, shake your head, gently move your head, rotate your head, both sides, very, very gently. Okay, then we'll start our lecture today, Introduction to Global Change. And this is me. My name is Bisal Sitola. I'm professor here at the Norwegian University of Life Sciences. I'm living here for last 33 years. Many of you are not even born, I believe, but I am the same campus that you have seen in that background for last 33 years. And I do teach, and also I've been working in many countries in South Asia, including Bhutan, Nepal, Bangladesh, Pakistan, Sri Lanka, Afghanistan, and also India, quite a bit, quite a lot really, around the issue related to different different dimension of environment and natural resource management. And I've been also working in Africa, like Malawi, for 5 years, leading a big, really national capacity building project on climate change. And also I've been working in Ethiopia for 8 years, leading the triangular project and very many things, watershed processes, water harvesting, and so on. And as you can see that both my accent and my face is not looking like a Norwegian. I am a native of Nepal. So it's very good that this is my very short introduction, that I'll be the course responsible for this. So today, just a soft start today, we'll have an introduction to global change. Let's start from the global change. You can see really this is a photo which is taken from the satellite. It is a real photo. It is not an artistic presentation here. And this is the home that we call, that we live from the space. It looks like blue and pulsating with the life. And this, the way the earth function in a very self-regulating way. And when we have been observing after the industrial period, of course, there has been a natural planetary changes that I will also introduce right away. But the global change by words refers to planetary scale change in our system. Okay. Our Earth system consists of, land or biosphere. We have a hydrosphere, oceans. Our Earth system also consists of this atmosphere that we'll talk about it, polar region, the cryosphere, and also all of their some sort of life, that is the biosphere. And then also this Earth system consists of natural cycles and also deep earth processes that will not cover in this particular lecture also. So our system is also now includes the human society, the societal influence, because the human being itself become almost like a geological force that will cover in the anthropogenic influence in the next lecture. So that is also a part of global change science, and all in all, a large scale change to different component of our system and also in the society. So as you can see it here, the global change talks about all these things that we are going to cover in future lectures around human health a little bit on the environmental degradation, land degradation, for example. Every minute, 10 hectares of land is being degraded worldwide. I have already spoke a little bit about biodiversity conservation, land is change, all this anthropogenic process like urbanization and also population, weather and climate, and so on and so forth. Let's take an example only about the climate. All information about climate is really, this is being updated all the time. 2020 started with Corona, so I have not seen those kind of reports, but just in 2019, if you look at the new insight around the climate change, you see that there are 10 new insights. There are really, they call it new, but whole thing is that every year a kind of surprise. The world is not on track. For example, greenhouse gas emission continue to increase despite all the convention agreement. So many kind of technology things are being all the time generated, the cars and this and that, but it's still record high. Also existing fossil fuel based infrastructure will, if operated during its full cycle, take world above 1.5. That means in the business as usual scenario, we know that this 1.5 degrees Celsius rise, at least in the earlier year, we are thinking that it will come by the end of this century, but the new record says that it is coming already in 2030, 10 years down the line. So the world is not really on track. You can go on and go on. The climate change is faster and stronger than expected, that I'll be showing quite a lot of them in this lecture and also in the subsequent lecture. The climate change leaves no mountain summit. You see, as I told you that I'm originally from Nepal and also Bhutan, and there are students here from Bhutan and so on. Glaciers are on an average estimate to have lost about half a meter in thickness per year in 2006 to 2015. Half a meter of thickness, okay? So this third pole, these mountains, for example, Himalaya, you can see the recent literature from Ishimod. This is also alarming. So like that, this kind of information that you can find internet here and there, forests are under threat with the global consequences. We know that one. Weather extreme, a new normal in 2019. You see, the extreme become now a normal. I mean, no more extreme, almost like no more extreme. The biodiversity loss, there will be a separate lecture on that. Climate change threatens to food security, there will be a separate lecture on that. And also so on and so forth. So these are new surprises, new kind of insights in 2019. And as you know that these things about global environmental change, you have to be more awake and see what kind of changes are taking place. And science is already there. The models are becoming more and more robust, because when I started my PhD in 1989, the model were not very robust, but now these models are becoming very robust. And you see that this is a temperature, the variation or anomalies from 1880 to 2016, okay? And you know that in 2016, at least until this model was run and they published the report by The National Oceanic and Atmospheric Administration, NOAA, in the United States, 2016 was the warmest year. And this is a kind of systemic change. You see, it's affecting every places. And if you look at this recent one in 2020, you see the global average increase is 0.92 degree, and the warmest March in the year 2016. And you see there is some variation, but it seems like if you take it all this variation and take a more average, almost we are expected to have 1.1 degree Celsius rise in global average temperature. Of course, if you look at the again global change of our biosphere, particularly this uh, land cover change 8,000 years ago, when the agriculture started almost like 10,000 years ago until now, the reality is like that. Thank you. So this rapidly changing world with growing disaster and disorienting dilemmas. On top of that, COVID-19 is again affecting every part of the world. And we all our scientists are again occupied with our own things, telling this story, updating the data. And if you look at these things that was published in 2018, again, without shadow of any doubt that global warming is likely to reach 1.5 degrees Celsius between 20 to by 2030, only 10 years from now, when I'll be completely retiring and you will be probably landing into a good job. Okay, just to show you these things in a little. So what will happen really? And there is that if you look at this IPCC report, which is being constantly updated and bringing more and more surprises, this is in the x-axis where there are the different type of threatened ecosystem, extreme weather event, and large scale singular events. When the IPCC started their first report in 2001, they think that the worst will come when the global temperature will reach around 5-6 degrees Celsius. But as you look at it, when you know more and more knowledge and more data we gather all over the world, no, this worst is coming. You see now this 2018, the high additional risk because of the climate change is coming. Already you don't need to wait until 5 degree or 6 degree rise, but already in even 1.1 degree and 2 degree, you can look at the processes a different kind of ecosystem, or you can look at the data from extreme weather event, their severity, their extent, their frequency. Here, it seems like even that we are thinking that historically they will come only when the temperature go as global temperature go as high, but no, it will be the same kind of risk, additional risk will come even sooner. So this is again reconfirming this kind of exercise. The IPCC, as far as I remember, there were almost 10,000 scientists all over the world working, very esteemed scientists, analyzing the data and bringing some kind of prediction. This is from my home country, Nepal, just to give you an insight. What is 1.5 degrees Celsius would look like in 30 years from now. And this, you see, in order to have attention, global attention that look, this fragile Himalaya is melting. The cabinet meeting of Nepal took place in the Kalapathar, this highest, where you can, not the highest, on top, the top is 8,848 meters, but here around 5,000 meter elevation in Kalapathar area, so that world will know that this beautiful mountain, which is our also global heritage, there is a melting of this snow and ice, and they are becoming naked and naked. But if we don't do something urgently, if you look at the estimate report and so on, by 2030, when global temperature will rise to 1.5 degrees Celsius, then if the same meeting will happen there, this beautiful mountain would look like this, or like a ghost, like a kind of object that side without any snow cover. So there will be a separate lecture on glacier meltings in this particular course. So all in all, in this very long time, the Earth was, last 10 or 12,000 years when the agriculture started, we have a long summer, which is called Holocene period. But it seems when we see that, when our major data say that from multi-location, that long summer with a predictable temperature, warm temperature, warm means that very suitable for the plant growth and agriculture, that kind of situation, that Garden of Eden, it seems like we are living that Garden of Eden. So it's because the human being have a very hard, the footprint is rather hard. IPCC says that the limiting global warming to 1.5 degrees Celsius would require a rapid, far-reaching, and unprecedented change in all aspects of society. Therefore, in this particular lecture, there are many natural science mixed here. This is not, we are not teaching you kind of natural science kind of things, but trying to bring awareness that really we have to really start looking back how the society is functioning and how our individual behavior, attitude, and everything influencing everything else, what we also call it in our wisdom tradition, this dependent origination. So incremental change, that some technology will do something, or bringing more electric car will be enough. No, that will not be enough, because every time we are getting these surprises that I have shown you. Okay. So now this Earth system science, little bit, will be of course talking many these crises or challenges in very much, but there are other issues. Global change is not only about the climate change, but there are also cultural extinction. If you look at the literature today, a few years back, there are reports, published work that every 14 days, one language is last spoken in this world. Now they say that every 3 months or so. But anyway, you see the rapid erosion of culture, language, their heritage, and many more things. Climate change, we also talks about. Pollution, you can talk, go on and go on. We have an entire course on pollution here. So, this microplastic problem. So just talking about problem became old stuff already, to best of my knowledge. I'm teaching this course for many years. Every time we have to just update those hockey stick like curves that yes, everything is going in exponential way. And even they come into this popular medias that you can see it here. This one example from South Asia. You see that number of threatened species. These are the hot spot. The hot spot of biodiversity. If you go to Indonesia, Nepal, Bangladesh, India, you see the number of extinct species different in different countries and different type of species in this color is just growing. I mean, it is almost 1,000 to 10,000 more extinction rate than the natural extinction rate. So there will be also a lecture about the biodiversity hotspots and also, so all in all, what I wanted to just bring your awareness is that the human earth is suffering because earth has human. For a moment, you can close your eyes again and just again focus on your breathing, breathing in and breathing out, breathing in, slowly breathing in and breathing out. So don't look at the screen for some time. Just contemplate on your breathing because that breath that you are breathing contains almost 10 to the power 22 number of atoms that is comes from everywhere in the earth. If you look at the global circulation model, you are really breathing in the ecosystem here. And when you are breathing out, you are also breathing out a part of the ecosystem. All the time coming in and going out. And this fresh air, which was available to you, free of cost, without, this is what is also changed significantly. So this is some kind of responsibility we need to have it. But for the time being, just give awareness to your breathing. Breathe in, count 5, it will energize you. And breathe out, count 5, it will relaxes you. Continue for a few, 1 minute or so. Close your eyes, not look at the screen. Breathe in, breathe out, breathe in, breathe out. No break between incoming and outgoing breath. Okay, you may open your eyes. So before we take a break, we'll have a very summary of what I have been saying. So what is really a global change? Okay. The global change is global scale changes that I have shown you many examples that are affecting the functioning of our system. I have shown you what is happening with the temperature, what is happening with the land use changes. Okay. So those, that global scale changes. And this is not only climate change, it's both biophysical and it's also global change science also talks about natural as well as anthropogenic changes. Like natural changes, when there is a big volcanic eruption, then it pumps out very many sulfate particles, and then it also provides some kind of global cooling transiently. Okay, that is not a man-made thing. But about anthropogenic changes, what has happened, what is happening now, we'll talk more and more. Also socioeconomic and biophysical changes. Many places, because of the resource extinction, the already conflict that was there become a reality, because when people already, because of the poor governance, poor kind of management, people were poor, and then there was a deep kind of dissatisfaction in potential. And when on top of that, when there is an increase in drought, extreme event, flood, landslide, you can go on, then it will also bring both social and psychological behavior of human being. So some of the historical example of hockey stick curve that we have been teaching for quite some time. You see, nitrogen fixation, for example. Nitrogen is fixed in plant and then ultimately go to the soil. And there is a natural nitrogen fixation. You see all the legume plants, and also there is a industrial fixation. But look at here, the natural fixation in this data before the industry began was but more or less the same. But the anthropogenic nitrogen fixation, when this big fertilizer factory started after the Second World War, and then they have to feed population, they have to feed military, and so there has been an industrial fixation of nitrogen fertilizer. For example, North Hydro was once upon a time 2/3 of nitrogenous fertilizer around the world they were supplying. So that is anthropogenic fixation, and this is going somewhere else, because when nitrogen is fixed, when the on-reactive nitrogen, the molecular nitrogen become a reactive nitrogen either through increased legume cultivation or anthropogenic other kind of fixation, then you'll see that. So temperature, we have talked about that. We'll talk into the greater detail. This is a global temperature. Species extinction rate is increasing, that I have already told you to. And then this atmospheric carbon dioxide. When I was a PhD student myself in 1989, when I started, that time the atmospheric concentration that I was using and doing also inter-laboratory calibration, it was 360 or 365 parts per million. But you see, during my lifetime, when my PhD student or you are will measure today, just in data from 2020, is that it is already, this hockey stick curve was going up and up and up and up without stopping, without bending it to already 415 parts per million. Ozone, there is some kind of good news about the ozone because of the Montreal Protocol and so on. This ozone, because since it was entirely this chlorofluorocarbon was anthropogenic, and there is a good international initiative to regulate them, their concentration is becoming much better for human. And you can go on human population. We talk about that quite a lot. You know, already 7.8 billion people. You know that when I came to this world, you can imagine when I was born, the population of world was only 3 billion people. It is now 3.8 billion. So you can guess my age. I will not tell you, it is secret. Okay. When the world population was 3 billion, you can check out in the internet. Nitrogen, I can tell you that was in 1960. Nitrogen in the coastal zone, you see, when more and more industrial fixed nitrogen come in, then it has to go somewhere, you know. That is the basic law of ecology, that if something comes in, it will go somewhere when it comes to the matter, when it comes to element. So more and more nitrogen fertilizer because of agriculture intensification, modernization, and then these things. And finally, almost 20, only when whatever fertilizer you apply, and when it comes to your food, if you are a vegetarian person, 24% that nitrogen you'll be consuming with that food uh, in amines or in a protein form. But if you are a non-vegetarian eating meat and so on, then that crop that you have produced, you need to feed animal and there is another loss. And finally, you will only consume 4%. So remaining huge amount that goes where it has to go somewhere, it goes to the finally the water body and to coastal zone. Okay, the forest, again the same story. The loss rate is 3% more than previous year. Whatever rate was before, it was 3% more this year. Like the size of Switzerland is being deforested every year. So what is global change? It is systemic global change. There are two types of global change. One is systemic global change. That means environmental changes which impacts the functioning of global system, like effect of greenhouse gas emission on global climate system and also ozone depleting substances. You know, for example, when the greenhouse gases come from soil or from industry or from automobile, it goes to the atmosphere, and the atmosphere is a global circulation. So it goes to the climate system. It goes everywhere. As I was telling that when you are breathing in that atom which is coming from everywhere, and if you look at the global circulation model, every 14 days at the atomic level, all that those atoms were passing through plant, animals. You can imagine everything it is passing through, and again it's recirculating around. So, for example, climate change is a systemic change and also cumulative global change. That means localized environmental change. For example, deforestation, which is happening heavily in Nepal, India, and elsewhere in Africa also. And when you put them together, then the effect is global. Okay, localized environmental change whose cumulative impacts are widespread or which impact a significant fraction of global resources, such as land degradation. As I was telling you, there is a separate lecture on land degradation. Groundwater depletion, there is a separate lecture. Species extinction, there is a separate lecture. So all that is what is cumulative type of global change. Okay. So the global environment, that was global change. Okay, but what is global environmental change then? Then just global environmental change includes change in the biophysical and biogeochemical environment. We'll talk about that in a greater detail, either caused naturally or influenced by human activity. For example, deforestation, widespread deforestation, burning of fossil fuel, and also consumption of this fossil fuel. Urbanization, you know, now today almost 60% of the population are staying in the cities. Agriculture intensification, I know it started in India long ago in 60s, but now we are also aspiring a sustainable agriculture intensification in Africa, how to feed that growing population, okay? And also the freshwater extinction. All these topics are a kind of global environmental topics, but they are interchangeably, we use a different terminology here. Global environmental change is also concerned with more than just a climate change and is set within the context of Earth system science. Just for an example, you know, global environmental change includes what kind of change, whether it is a cumulative change or if it is a systemic change, and what kind of impacts the global environmental change will have at a different level, at a microorganism level, to the plot levels, to watershed level, to landscape level, and you can go on and go on. So impact in very many different level have a different methodology. And also the synergy means that these days synergies are even more important, because if there is a climate change going on in one side and biodiversity is going on the other side, and both have an impact on ecosystem processes, okay? So if we examine individually what is the effect of a climate change separately on that ecosystem project process, you get one number. Let's say nitrification, denitrification. You can choose any one ecosystem processes. And what is the effects of, let's say, biodiversity or land use changes? You get another number. But if you look at what is the combined, if in the same place, the climate change is also happening, biodiversity or land use change is also happening. The combined effect is more than the individual effect. That means 2 plus 2 is not 4, but it can be 5, 6, and so on. And that is what is, you can say that after a tipping point, it behaves, the system behaves very different way, not linearly. And what are the current state of knowledge or impacts? Because it's being all the time updated. That is also a topics that we teach in global environmental change. Some of this biospheric and atmospheric interaction is poorly understood. That's why many things like climate surprises. There is a term between climate change, climate variability, and climate surprises. Climate change is over a change in any kind of rainfall temperature over more than a decade. And climate variation is a variation within this, what happens. But surprises means that you have never been experienced before, but now you are experiencing that, coming as a surprises. And these surprises are becoming so much that now they are also becoming no more surprises for many of the things that we'll be also talking. So degree of certainty, gap analysis, what are the knowledge gap which are there, what is not known, because as I say that the atmosphere and biosphere, that interaction is poorly known. There is a lot of gap, lot of black boxes are there which we need to also look at when we're talking about global environmental change. And what are the international responses? Okay, historically what has happened, how the international community identified the problem and how they're responding now, and what is the changing dilemma there. Some of the new leaders are coming and say that, oh, this climate change is just a construct of people who do not have the scientists who want to have funding and so on. So like that, and then even furthermore, this planetary boundary or safe operating space, where we are heading, how close to that danger we are approaching, about the planetary boundary and so on, that we'll also talk in this one. So with this, I'll give you 10-minute break. You stretch your leg, you can go to toilet and you can do anything and we can come back and continue recording. I just pause the recording now, okay? Thank you. Okay. Okay. So now I will start again. Please come back. Okay. Okay. Welcome back. I think we'll continue here. So in 2009, in order to really see that which environmental processes have been influenced so much that they are going almost out in a safe operating space. That means that Earth has its own buffer power to, if something goes wrong, it tries to fix it and repair it. Earth has its own intelligence. If you look at the Gaia theory and other theory. So the safe operating space, this planetary boundary. And again, it has been updated all the time. And now, since 2009, they have been bringing many things that will be also teaching in a understanding this kind of system in a very many uh, different lecture and courses here. In 2009, as you can, 2019, another paper was also published around it that you can also read it, you can find it. But the whole purpose is that before even I talk about that, what is a planetary boundary? Let me give you this example and then I'll come back. Let's say we know that carbon dioxide is responsible, one of the important greenhouse gases, and also contributes to almost 54 or 55% of predicted global warming. And this concentration is increasing. And it has a implication for, uh, of course, temperature rise and also extent of land ice. If the temperature is increases, the ice start melting in the land and so on. So here, the thing is that as long as before the industrial era, when the CO2 concentration was only 280 parts per million, and then you go on increasing that CO2 concentration, and then until 350, you can predict it linearly. Okay, the concentration is increasing in this way, and ice is melting at this rate because of the very complex feedback effect and so on. But after it reached 350, which has passed long before even I started my PhD, then the things, for example, the extent of land ice, the disappearance of that one by increasing carbon dioxide is not linear. Then it start behaving in a different way because that kind of threshold or tipping point was reached. And then it start behaving in a very different way, the faster rate than those linear model could predict. So that is what is a planetary boundary. After that, then there is a uncertainty start because the whole melting rates and this and that, this is not following any more linear. It has starting melting in exponential ways. And then that is a boundary where until 350 it was safe because Earth has that system to bring it back. But after 550, that is a long way. I mean, then you never can even predict how the system that even those models that you are running now will not be a kind of predictable, and that is very, very unsafe, and we cannot say anything. So that is what is planetary boundary, and that is, I gave you the example of climate change, and they use control variable like the CO2. Those they have a data at planetary level. All these like biospheric integrity, land use system, this until they are in the safe. But some of the, for example, land use changes it so fast because of the deforestation that it is again going out of the comfort zone. And I'll be talking a little more on that when I teach you about this particular concept. But here to introduce is that humanity has never faced a challenge like this before. Okay, this is a very recent phenomena. In 1 million years, losing one or two species is normal. But now the rate of extinction is so fast that this biospheric integrity, if you look at this control variable that is verified from different major data, it is alarming. It is never like before. So avoiding abrupt shift will require social transformation like we have never had before. Okay. So Now, a very basics of our system, because today I have talked quite a lot about the global change, but let's see from a very purely a kind of natural science kind of perspective. We live in an interacting earth, which is there are interacting physical, chemical, and biological processes that transport and transform material and energy, and thus provide condition necessary for life. What comes, what goes, and that is a dynamic equilibrium of this transport and transformation from one pole to another pole, one flux to another fluxes. So, so the Earth system science, which is quite new, the Earth system science is application of system science to the Earth. In particular, it considers the interaction and feedbacks through material and energy fluxes between Earth subsystems, cycles, processes, and spares. So what happens in, for example, biosphere will have implication for atmosphere. How? One example, for example, when you take away the forest, simply you can quantify that. There are very good model and very good satellite data, the GIS model that predicts that in which rate it is going on around the world. And that means at the same time, what is happening there is that the forest is a natural sink of CO2 because during the photosynthesis, it captures and it binds CO2 and creates a biomass. That is what is also a carbon sequestration, because then some of this carbon which is there in CO2, which will be converted into a very lignin, these bodies, the plant body in a long-lived pool, and therefore it has, so it's a biosphere atmospheric interaction. More you clear the forest, less the sink strength of the forest will be there and more CO2 will be left. Okay. So all these, so this is a study, the Earth system science studies of interaction between ocean, atmosphere, living system. I just gave you one example, atmospheric and biosphere. Similarly, the ocean circulation, different kind of geological processes, land surface dynamic, all are interrelated, and also now the human system, because it itself, the anthropogenic activity, the Anthropocene, anthropogenic era itself is a kind of geological force which is affecting Earth at a systemic level. Also, Earth system science is that study which study the processes that connects biological, physical, and human system operating near the Earth surface. So these are the definitions that you can find anywhere. It is also a study of how interrelationship between physical and biological system impact each other and leads to changes. Okay. And this kind of things that we will be going through very many different lecture here, how hydrosphere, there is a kind of how the exchange between the hydrosphere and biosphere at a global level is really affecting the growth, affecting the biomass in the earth, how the geospheric and atmospheric processes, geospheric processes, for example, the nutrient cycling and so on. So all these are linked, and they requires now, because of the power of computer, when the knowledge is growing, and there one can predict if something happens in one system, how it has impact the other system in a more and more robust way, I would say. But so in a very basic way, the interaction between atmosphere, hydrosphere, lithosphere, biosphere, cryosphere, and anthrosphere. For those of you who have a very, I mean, some come with the art history here in our program, some comes with journalism and so on. These are some of the slides you can read yourself what is atmosphere, because these are the different spheres of our system science that we'll be studying in a greater detail. Lithosphere, the Earth's solid surface, often called the crust of the earth. Okay, it includes continental and oceanic crust as well as the various layers of the earth interior. Biosphere where the people lives. You see this forest, the biology, the life, all life on earth, including men and all these organisms that we share this earth. The life zone on our planet distinguishes our planet from the other in the solar system, at least. You see this blue planet. And cryosphere is also very important when it comes to our system science because the objectively verifiable data are from the cryospheric research. The glacier melting rate can be really measured in a very with a great precision. Okay, all the changes in the snow, ice, all these glaciers, ice shelves, icebergs, and Arctic climatology. It has been studied, and also in the third pole, for example, the Himalayan region, Ishimori is doing a lot, very many study, and there is a separate team of cryospheric research. Okay, the frozen part, the portion of the Earth surface where the water is in solid from that is your cryosphere. Western Antarctic, there are alarming data these days which have come where this melting of West Antarctic definitely within this century, 1 meter of sea level rise because of the melting is inevitable. And then comes the anthroposphere. Anthroposphere, this is again term utilized by Paul Krugman, Nobel Prize winner. So man and his direct ancestor where they live and human population and its building, dam and other constructions. So now at the level of our system, let's look at the temporal variability so that we can understand to some extent. There are variability, both diurnal variability, daily variations, seasonal variation, yearly variation that one can measure different ecosystem processes, let's say carbon dioxide fluxes, nitrous oxide flux, methane flux, okay, photosynthetic kind of regime and the change in that one. And these, if you put them together, they become a rather complex system, okay? And they have a variability and both stability. What is observed is stable at one scale is variable at another. For example, weathering of rock. The weathering, if you look at just in 100-year scale, it's more or less, it's there. It's not changed. But if you look at the 10,000 years scale, it is also a kind of a variable. And when you look at the climate itself, one example, the climate, what is happening to the climate, you can see that climate as an example, the 4 last glacial and interglacial period. If you look at just data from last 4,000 years, there is a pattern which is repeating here. For example, this is based on this concentration of greenhouse gases is based on this Vostok ice cores, the ice that has been tracked in a paleoclimate, deep buried from Antarctica, and you can use proxy, the isotope there to really estimate what was the carbon dioxide and methane concentration in last 400,000 years from today. You see, here, this side red is the temperature, the CO2 and methane, these greenhouse gases. You see, when the temperature is decreasing, they were also decreasing. When temperature was increasing, they were also increasing, something like that, because of Earth have a complex feedback or intelligence to buffer. Because if the temperature go on decreasing and decreasing irreversibly, then of course there is no chances that anything could happen that will support life afterward. But because of this variation and stability and between this glacial, where this temperature is going down and the interglacial period between the two glacial cycle, then you see that there is a buffer, there is a earth intelligence that is putting, there is a feedback from the earth that way you should not go that far down. Again, things happens and then it comes up. But the problem is that if you look at now data, not from 400,000, but bring it down to 100,000 year back, then you see that people were, the temperature, this is the isotope, and this is the temperature. Isotope is a proxy of these greenhouse gases, as I have said, and this is the temperature changes. They were, people were coming in a different era. People arrived in Australia, but somehow they survived in the caves and so on. But the good news is that that Garden of Eden that I was talking about, this was last 12,000, 10,000 years, this one, where the agriculture began in somewhere in the Middle East or some also in the New Zealand and that area. And that long summer, you see the temperature is more or less stable here. And that was where things was predictable, weather, climate was predictable. That Holocene period is the period where they call is the time. And the same thing, if you look at it, it is a little more close way here. This is a glacial period. It started here, but this is a kind of interglacial period here, where Earth was in kind of some kind of small equilibrium up and down during the Holocenes. And then we are here, almost here now. This scale is the time scale. In the earlier, you see here, Earth was, of course, there was, if you go back to a million-year scale, there was a lot of turbulent time. The Earth, the whole surface was buried in meters and meters of ice. But then it was again coming back. But during the Holocene period, it was not that kind of turbulence, you see. So now Earth was stabilized in certain kind of equilibrium. This side is the stability during the Holocenes, that 10 or 12,000 period. But now the planetary threshold is reached because of human emission of greenhouse gases. So from this Anthropocene, when the Anthropocene is this almost a geological epoch begins, then either we have a choice that we do something, we don't increase that temperature that was there, that was destabilizing the Earth, and we reach to the stable state, so it is just dancing in a certain level of fluctuation. Or if you continue in the Anthropocene with the business as usual scenario, with human emission of greenhouse gases and biospheric degradation, then this planetary threshold is reached. Earth cannot, this is beyond the Earth capacity to buffer itself, and then finally it reaches to this ditch. That is called hot house Earth, which is a kind of, so same thing, this is bit things, if you look at this other data about temperature, you see, again, this is glacial and interglacial cycle. In the interglacial cycle, when there are more or less not big turbulence, that Holocene period, but whole these things is affected only after the Industrial Revolution in 1950. You see the Anthropocene, okay? And then finally, that is where the temperature started growing, increasing during the Anthropocene, and then finally it is all set. We are here, but we are all set to cross this limit of planetary threshold. In another way, you can also look at it that in this side is the anomalies or variation in temperature. This is the variation from the global average temperature, okay? So If you look at this earlier paleoclimatic data and the temperature proxies for temperature and greenhouse gases, there has been a variation, but it has never gone exceeded in entire thousands and thousands years back that we can have those proxy data, that only there was a variation but never exceeded 2 degrees Celsius. In last 3 million years, there was no higher all the way to 3 degrees Celsius, or 2 degrees Celsius, I mean. Last before 3 million years, yes, because this earth was undergoing very many of those kind of changes. So this 2 degrees Celsius, by the end of this, even it will come by the end of this century, will experience something that has never happened for last 3 million years. So all in all, this is just to summarize that the seeing Earth as an integrated system of process is a quite novel idea. And we have also summarized it that this consists of Earth have this regulation, feedback regulation, because it has different kind of spheres, and this in a very complex way, they are very linked in a cybernetics, this is a transdisciplinary approach of exploring regulatory systems, their structure and constant, that is, and also possibilities. That is what cybernetics is all about. Okay, so many negative feedbacks. If something goes exponentially wrong, then Earth fix and try to regulate from the process level, from the intake level, and so on. So in this system, we'll be talking more about how this different system, integrated system of processes, is quite a novel idea, and that we can also study through studying the hydrological cycle, carbon cycle, nitrogen cycle, that we'll do in a greater detail in the ecosystem processes relevant for atmospheric chemistry and global change in future lectures. There are very many different kind of processes that we'll not be studying in this particular course, about the geological processes, about different kind of gravitation orbit, and the change in the Earth orbit, and different kind of these things. We'll teach a little more about some kind of processes, ecosystem processes, including some oxidation, microbial oxidation, and some biological processes in a greater detail in one of the lectures. So this Earth system science, in order to understand it better, we need to know a little more about the biogeochemical cycles. In our system, a biological, biogeological, biogeochemical cycle, or substance turnover, or cycling of substance, is pathway by which a chemical substance moves through both biotic and abiotic atmosphere and hydrosphere and different other component of the earth. That is what is biogeochemical cycle. As you know that the energy comes one way from earth as from sun. Sun is emitting the energy that comes from there, but it is one way. But when it comes to matter, which is available here, the element like carbon, nitrogen, it just goes from one pool to another pool, to one pool to another pool. Even you can look at yourself. When we die, we'll get decomposed or born. Then what happens is that if you are getting decomposed, our body, that carbohydrate, when it decomposes and finally give the CO2, and CO2 go to the air, right? And then that CO2 is utilized by the plant. So it's just turning from one pool and fluxes to another pool of fluxes. This is from biological to abiological to biological to abiological, biotic to abiotic, and abiotic to biotic, that way. So we'll be also learning about it. So a few words about the Earth system observation, a system of systems approached by NASA. So what they do really is that in order to study our system, which is a system of a systems. All these, as I described, hydrosphere, biosphere, lithosphere, these are different systems. And as you can see in this graph here, that you see, particularly NASA, wherever there are good science around it, like you can start with carbon cycle is very thoroughly studied, and there are very many data even at all the way to global level. Uh, that there are observatories which is measuring CO2 uh, concentration in atmosphere with so many interlaboratory calibration. There are also climate variability data now. There are more and more those good data are coming, and also the weather. They also bring some of the processes that takes place in the Earth surface and both interior, both pedospheric process and also lithospheric processes and atmospheric composition. This is also science is growing. So when they have a good set of data from around the world, then they can do some kind of Earth system science. Again, to recap, the Earth system science is a study of how scientific data stemming from various fields of research that is shown here, such as atmosphere, ocean, land, ice, and others fit together to form a current picture of our planet as a whole, including the changing climate. Okay, just example. Um, uh, the example is that you see there are Earth system models, different types of Earth system models. First, you need a observation or data. Okay, that starts from there. So whatever research has been done, whatever funding is available around the world, they publish, and the data also comes from there. And these data will be fed, these observation is fed to these Earth system models, which links one sphere to another, to another, to another, and then provide some kind of prediction, for example. And it has to, this prediction also need to pass through a decision support tool. How, in which way it will be presented about the climate, weather, about the ecology, ecosystem processes, about the what kind of disaster, early warning systems, and also information to agriculture, and what is going to happen in human health issues. For example, if there are, if there is anticipation of warming in certain part of tropical and subtropics, the mosquito breeding will be also enhanced, and that has an implication for human health. That will be also talking, and all other component in the Earth system. So more, garbage in and garbage out. As long as they have a good data with some kind of predictability, robust data, and if there is a process understanding, then this becomes better and better. But as I say, that there are many surprises, because some of the processes that these models were taking as a kind of linear thing, but becoming non-linear, and even it cannot be predicted, and all coming as a surprise. That So these things that you can read, that the recent example of the climate change on land, and this text you can read yourself. And this is also to just to show that global surface temperature uh, is is changed through the warming, and it will continue in all RCP, means representative concentration pathway, meaning that certain greenhouse gases and certain assumption how what kind of pathway it takes place. So the RCP 2.6 is that only 2.6 watt per meter square of warming. You need to read this literature around it, but 8.5 RCP is the most dangerous ones. That means 8.5 watt per meter square of warming over a period of time. By the end of the century, what is really going to happen? This we have talked about. We have a data now that, the Arctic Sea ice in September could be gone by 2050. You have seen those photos of uh, polar bear and so on. Sea level will definitely rise. As I was telling you, that some model says 1 meter, other models, other may in different RCP scenario. When I was teaching last year, that I was teaching that, oh, atmospheric concentration is 4.8 atmospheric concentration of carbon dioxide, which is far higher than when I was myself was measuring 30 years ago. Now this year, if you data, it is already 2011, 2011 or 2012 or even 2014 in February 2090. Okay, these are just different kind of example. The problem is that, you see, the way the society, the way the academics, the way the different, even within the human being, and the way it has evolved in a different context, in different kind of arena, there is a problem that the science system science is also facing. Despite the fact that there are robust data available, there are little type of denial and counter claims, because always you can, because there are, if some uncertainty, you can always say that, oh, the climate is not happening. Okay, there are some there, including the big leaders, even the leader of superpower is still not convinced that there is a climate change going on. There are interpretive kind of denials where they, okay, climate is changing, that we can see, we can feel, we have a good science, but they give that, oh, it may be not because of we are using the car or our behavior, we are consumers, but more they give is maybe because of the change in the orbital eccentricity, or the change in the solar radiation, something which is not our fault. But there are other kind of denial, like implicatory kind of denial, that we have the knowledge, but doing a right thing with right knowledge is not a part of our everyday life. Okay, so therefore it's very important that we cannot afford this. We need a transformation that we'll be also teaching toward the end. So all in all, toward the end, what I'm saying is that there is a persistent gap between the aspiration and reality. In one hand, we are teaching this course with the aspiration that, well, we are able to deal with this problem, we are able to do anything which is possible to mitigate the environmental degradation, environmental change at different scales. But every year, the reality is that no matter whether there is a Paris Agreement or there is any other kind of international agreement, which is every record high thing. We also try to teach and putting this even in a very nice poster around the corridor about the SDG as a hope and aspiration is, in fact, this is an aspirational goal. This SDG, I believe that like this MDG didn't work out, this SDG also is good to have aspiration, because human being is a goal-seeking entity. But look at this, what is happening with this aspiration of SDG from different country, in South Asia, Afghanistan, Bangladesh, Bhutan, all these things that you can read yourself, that most of the thing is the very high challenge to get this goal, to achieve this goal. Some of the things have a moderate, but some of the goals have relatively easy in different kind of situation. So the progress is very little progress in Asia Pacific region about these what the SDG. But even if you look at the developed country like New Zealand and so on, and this arrow says that which is these are the different scores, which is this, some are even decreasing than before. These goals are, instead of going that way, it's going to the negative way. Some are stagnated, depending upon the CDC years. But most important thing here is this, where and where the Earth system science lies on this biosphere, this big pie here. And there we must do something. Otherwise, the world will not, our children will not be able to see. So therefore, the Earth system science, which talks about the land, which talks about the forest, which talks about the water, is a major part of the pie here in this particular. So now we are trying to link here this the development goal, the sustainable development goal SDG with these things, and you can also see what is really happening. So there are some good news also, particularly in developed country like SDG 8 and SDG 9. So all in all, the take home message is that our system can be understood as a system where life itself play important part in producing and reproducing its characteristics. The variability, but within a limit prior to human influence. Okay, even after influence, we have even all set to increase that temperature that never Earth has experienced for last 3 million years. Okay, this again a complex system or system not easy because of atmospheric biospheric processes are very difficult to understand really. And nevertheless, the system has gone through substantial changes as we have seen, and human influence must be seen against the variability of the system. You people also need, you can read this is posted, and I'll also send to other students. There are some very nice video about what is Earth system science. So from this entire lecture, what I do is that if you are able to just find answer of these two questions from this lecture and also from the reading material, you have done good job. Okay, because in the exam, since this course is so much diffuse, at least from this lecture, what is Earth system science and describe Earth as a system and nature of global change, you are in good hand. So with this, I will stop here. So if you have any questions and something, I will try to stop screen sharing, and then I will unmute, uh, allow participant to unmute themselves, and I will not like to record. So let me just first stop recording, stop live stream here.